Okay, so for this question, it says use the graph to estimate the stress in the cable at its elastic limit. So it's somewhere around this region, right? And we need to look at it's more or less 250, I would say, right? More or less 250. So 250, the elastic limit is below the upper yield point. So it is definitely below 275. So it is, I would say, it is about 250. Now in the mark scheme, it says 230 plus or minus 40. So the minimum value for this is 190, 270. So 190 is about there, and 270 is about there. So that is the answer. Now, by calculating the maximum tensile stress allowed, suggest and explain why the working load allowance is 1.1 times 10 to the 6 newtons. So, stress is force divided by area. So, force divided by area. You're given that the maximum load allowance is that. So, let me just rub out some of these first. So, we need to work out the area. You're given the diameter. So, the diameter is twice the radius. So, the radius is 0.045 meters. And you would do 1.1 times 10 to the 6 divided by pi r squared, 0.045 squared. And on the calculator, you should get 172 times 10 to the 6, or maybe 1.72 times 10 to the 8, same thing. So your answer, hold on, sorry, 173. So your answer should be 173 mega pascals. So that would be 1 mark, and because the maximum, what is the maximum? Well, we did say that it. Well, we said it was 250, isn't it? So 250 megapascals is bigger than 173 megapascals. So we have 250 megapascals is bigger than 173 megapascals, and it will not stretch too much. So not stretch too much, not stretching. And there's less chance of permanent deformation. So there's less chance of permanent deformation. Calculate the change in gravitational potential energy of the mass when it comes to rest in its equilibrium position with length 25 centimeters. We know that the original length is 20 centimeters. So what is the extension? 25 take away 20 is 5 centimeters. Convert that into meters, we have 0.05. That is the change, that is the extension, isn't it? Extension. Because it's asking you for the change in potential energy, we're working out the change. So here have the mass is 0.6 times, we are taking a g as 9.81 and then times that by 0.05. And your answer, you should get 0.29 43 joules. It's just better to do it in the 2 significant figures, so it will probably be better to write down 0.29 joules. And that is the answer. Show that the elastic potential energy in the stretch spring in its equilibrium position is 0.5 joules. So we know that elastic potential energy is either half kx squared or half fx. So half fx, now we know that F is ma, in this case it's the weight of the load. So you do half times 9.81 times 0.6, and we know that the extension was 0.05, and you should get 0.15 joules. And yeah, so you get 0.14715 joules. A student compares the values calculated in A and B, concludes that the energy is not conserved. To say that the energy transfer that occurs as the spring oscillates and come to rest, explain why the student is wrong. So we need to say that the gravitational potential energy is converted into elastic potential energy plus the kinetic energy. And we have elastic potential energy is converted into gravitational potential energy plus kinetic energy. So this is when it's falling, right? Because when it's at the top, because you are compressing the spring, the compression means that you're storing the energy. But also when it's this is when it's falling. So when it's falling, you're stretching the spring, and there is an extension. And because it's falling, there's gain in kinetic energy. When it's rising, the elastic potential energy, because now that it was stored, now that it goes back into gravitational potential energy because it's rising again, and it gains kinetic energy. So in both cases, remember that in both cases it will have kinetic energy because it's moving. This is rising. Whenever it is rising, the GPE will go up. When it's falling, GPE will go down, but then that's converted into elastic potential energy. And then the last point, you can say that the energy is dissipated as heat into the surroundings, right? Surroundings. And describe the main physical properties of this material. Number one, you have to say that F is not equal to Kx. What that means is it does not obey Hooke's law, so not Hooke's law. Number two, you can say it is elastic, right? It is an elastic material. It is an elastic material. It does not obey Hooke's law. And also, you can say that the loading is not the same, so it's not equal to unloading. Okay, so for this question, it says to calculate the extension of the metal strip when it breaks. So stress is equal to force divided by area, and you have the force as 16 newtons divided by pi r squared. Oh, we don't need pi r squared. It's so here you ignore the long, so it's just 1.2 centimeters. So 0.012 times 0.018 times 10 to the minus 3. Force divided by area. So that is stress. And we know that the Young modulus is that much. Right, so let's just work out the stress first. So you should have, on my calculator, I get 74 times 10 to the 6. And you're given that the Young modulus is that, so the Young modulus is 74 times 10 to the 6 divided by delta L of L. So we want delta L of L, right? Delta L of L is 74 times 10 to the 6 divided by, in the question is 7.1 times 10 to the 10, and that is equal to so once we have that fraction, we need to work out delta L, don't we? So delta L is equal to L times that 1.04 times 10 to the minus 3, and you know that L is 15 centimeters, which is 0.15 meters times 1.04 times 10 to the minus 3, and you should get about 1.6 times 10 to the minus 4.
Okay, so the assumption is that Hooke's law is obeyed.
Calculate the breaking force of a rod of radius 0.6 centimeters made from the same metal. Now, if it's made from the same metal, it will have the same breaking force. So, let me get rid of these working out. Okay, so I don't mean the same force, I mean the same stress. So the stress should be the same, of the same material. So you don't know F, so let me just write that down. So F is unknown, and the area 4 pi r squared, 0.6 times 10 to the minus 2 squared, and it's equal to the same stress. Now the stress that we worked out in the previous part was 7.41 times 10 to the 7. So rearranging all that, you should get F is equal to, let me just put this into the calculator. Okay, so your answer should be 7.41 times 10 to the 7 times pi times r squared, and so your breaking force is 8.41 times 10 cubed. Okay, so one of the questions was to define the spring constant. F equals kx, rearrange, you get k equals F over x. So the answer is force per length. It's nothing to do with stiffness. Yes, it does measure the stiffness of the material, but the definition is force per length, or you can say force per extension.
Okay, so make sure you write force per extension. Force per extension.
Now the equation, the question, where you have a load supported by two identical springs, here the extension is halved because the force is shared. So the tension is T over 2 in one of the springs, tension is T over 2 in the other spring, and so therefore you have halving of the extension. So the tension in each spring is halved, so the extension is also halved. The question is, explain why the force constant of the parallel arrangement of springs is twice the force constant of one spring. So if the tension is halved, then the force constant is doubled. Okay, describe the behavior of the wire when the strain is less than 0.05%. Before 0.05%, it is a straight line, so it obeys Hooke's law. And then it says the strain in the wire is 0.3%. Describe what happens to the wire when the load is removed. So in that region, it is plastic deformation. It won't go back to its original length. And then for part 3, explain whether or not this suggestion is correct. No, because you can only work out the Young modulus if you're using the linear region, because that is when it obeys Hooke's law. Right, describe the difference between longitudinal and transverse waves. Now for this question, you need to say vibrations or oscillations. You can't just say it is longitudinal is parallel and transverse is at right angles. You need to mention the word vibration or oscillation. So longitudinal waves are vibrations parallel to the energy transfer, and transverse waves are vibrations or oscillations parallel, sorry, not parallel, at right angles to the energy transfer. Determine the amplitude of the signal displayed on the oscilloscope. So here you've got 4 squares above the equilibrium position. So that's going to be 40 millivolts. 4 squares above the equilibrium position. So each square is 10 millivolts in the y direction. The frequency of the sound wave is equal to 1 over t. That should be 1 over t. So frequency is 1 over t. So 1 over 1.5 milliseconds, you need to convert to milli, and you know milli is 10 to the minus 3, so you get 667. For part 2, use v equals f lambda, so you know that the speed of sound is 330, if worked out the frequency was 667, so lambda is equal to 0.49, just rearrange, you get 0.49. Describe and explain how the signal displayed on the oscilloscope will be different. Here, the amplitude is smaller because the equation intensity is proportional to amplitude squared. So if you have 1 over 4 is equal to 1/2 squared, because the question is intensity is a quarter, that means the amplitude is halved. Amplitude is halved. So amplitude is halved. Amplitude halved. Determine the wavelength of lambda. In the diagram, wavelength is, so this is not a wavelength, right? That is half of a wavelength. Wavelength is when it completes one cycle. This is not one cycle. One cycle is, because it undergoes positive and then negative region, and then here you've got positive and negative. One cycle is positive and negative, so that's one cycle. So the wavelength here is 4 centimeters. That's one wavelength, 4 centimeters. Explain why the intensity of the wave changes as the distance x increases. So the amplitude decreases. If you use the equation, amplitude is proportional to the amplitude squared.
I mean, intensity is proportional to amplitude squared. Intensity.
When A goes down, that means I will go down. For this question, the wavelength is equal to, if you use the equation of V equals f lambda, so lambda equals V over f. So lambda is equal to V over f. This is the speed of light. Remember, it is the speed of light because it's of microwaves. Microwaves is in the electromagnetic spectrum. So rearranging that, you get 0.027 meters. Explain why the receiver now detects microwaves. First of all, it diffracts, and the wavelength is similar to the width of the slit, because now you have 2.7 centimeters, right? That's 2.7 centimeters. Here, intensity is power divided by area. You're given that power is kilograms meters squared per the inverse cubed of seconds. So when you divide power divided by m squared, the m squared will cancel. You're left with kilograms inverse cubed, s to the minus 3. For this question, you work out the total horizontal components, the total vertical components, use Pythagoras, and then you can use trig. So here, the vertical component is 1.3 because it's 2 sine 40. Because you're working at this part here, right? The vertical component is opposite the angle. And the horizontal, 5 plus 2 cos 40, you want this part. So 5 plus 2 cos 40. And then use Pythagoras, you end up with 6.66 newtons. Calculate the angle between this resultant force and the force of magnitude 5 newtons. So the resultant is this force here, right? That's the resultant. The 5 newtons is this one, so you want this angle here. So you can use tan. 1 over 3 divided by 6.53 inverse tan, you end up with 11.1 degrees. Alternatively, you can use the cosine rule. So you need to move this vector, the vector where that says 2 newtons, right? You move the 2 newtons to here, and you know that this angle is 140, that's 5 and that's 2. So you use 5 squared plus 2 squared, 5 squared plus 2 squared minus 2 bc cos A. So here you have 210 times cos 140. You still end up with
Okay, yeah, so ignore the a squared, that should just be a, but it's still 6.66.
6.66 newtons. And then if you want to use sine rule, you can get the angle. So opposite the 6.66 newtons is 140. Opposite the 2, the one that you want to work out, is the 2 newtons. That's 2 newtons. So sine 140 divided by 6.66 is equal to sine x divided by 2. Rearrange, you should get x equals 11.1. Right. Going up the slope is P. Because the question says sliding down the plane, friction is acting up. So P is acting up, friction is acting up. The only component acting down is the weight. So mg sine theta. Putting all of that into the equation, you know that it's in equilibrium. P plus F is equal to mg sine alpha. You know that P is 100. You know that F equals mu r. And I'm just substituting the m as 20. Now R is mg cos theta. In this case, theta is alpha. So 100 plus mu r is equal to 20 g cos alpha equals 20 g sine alpha. You divide both sides by 20, in the end you end up with 5 plus mu g cos alpha equals g sine alpha. Now for this question, here now it says sliding up the plane. If it's sliding up the plane, that means friction is now going down. If you compare the other question, sorry, the other part, the previous part F was going up, the second part is going down. Okay, so P going up the plane equals the two forces going down the plane. We know that P is 150, and that's going up. Going down, you have 20 g sine alpha plus the mu r. Now the mu r is the same as mu mg cos alpha. You know that m is 20, so you just put all that in. Okay, so I forgot about the mu. Have a look at the mu. So the mu should be with the cos, but the thing is that they cancel out anyway, so the mu is pointless. But to be technically correct, the mu should be there. Now, if you remember the second part, I'm just going back to the previous slide. So now I'm just putting down the equation from the previous situation. In the previous situation, the alpha is constant in both cases. So we can use the other equation from the previous situation. So in the previous situation, you got 100 is equal to 20g sine alpha minus 20g cos alpha. Okay, so this is from the previous question. And I'm just putting it into the form similar to the one above. So now we can add both equations together. You end up with 250 is equal to 40g sine alpha. If you look at the plus and the minus g cos alpha, they cancel out. Now, for this part, the weight is 4.5 newtons. It's going down. You've got horizontal force. Here, in this diagram, I'm going to the left. You can do it to the right. The resultant force is the dotted line going diagonal. So F squared plus 4.5 squared equals 5.8 squared. F is equal to 5.8 squared minus 4.5 squared. And you get 3.7, which is B. Because in the question it gives you the resultant, and you need to work out one of the forces. So it's a takeaway, not a plus. In this question, calculate the total vertical force supplied by cables A and B by resolving the tensions A and B. So the A is, you want the vertical component of this force, and you want the vertical component of this force. So here you would have 68 sine 10, 87.4 cos 50. You add both of the vertical components to give you the total vertical component. Calculate the ratio of the extension of cable B divided by the extension of cable A. Now, your Young's modulus is stress divided by strain. Stress is force divided by area. Strain is extension over the original length. If you put them into one single equation, you get force times length divided by area times extension. Now, in the question, it gives you the same length and the same cross-sectional area. So I'm going to get rid of the L and the A. So the ratio will just be delta L equals the Young's modulus divided by force. So the reason why I've got rid of the A and the L is because when you divide one by the other, you're going to cancel out. So, and the only two things that are different are the Young's modulus and the forces. So if you look at the ratio of the extensions algebraically, the extension of cable B divided by the extension of cable A is equal to Young's modulus of B times the force of A divided by the Young's modulus of A times the force of B. Now, in the question, you're given the Young's modulus of B is 1.29. The Young's modulus of A is just E. And in the previous question, you have 68 newtons and A is 68, B is 87.4. So if you substitute all that in, 1.29 E times 68 divided by E times 87.4, you end up with approximately 1. Right, so this one, F is equal to W sine 30. For this question, you need to write down the weight is equal to mg. So if you look at this diagram here on the left, so the friction is equal to W sine theta. If this is an equilibrium, so the W sine theta is the force going down the plane. You know that W is mg, and in the question it gives you 8 kilograms. So 8g times half, sine theta to half. You end up with F is equal to 39.24 newtons. R is equal to W cos 30, and you know W is mg, so that is equal to 8g times cos 30. You should get R is equal to 68 newtons. And then here, the work done per second. So force times distance is work done. Now, but here it says in the direction of travel. So in the direction of travel, you need to use cos 30. So force is 220, because it here says 220 newtons, times by the distance traveled. Now it says per second, work done per second. So you need to do 1.8 times 1. 1.8 times 1 is 1.8. 1.8. Now the cos theta is included in this part. So if you do 220 times 1.8 times 1 times cos 30, you end up with 342.9, which is C.